Now this part of the story is about one way mechanical energy, kinetic energy, can be converted into electric potential energy. Now if you recall, potential energy in general is about energy stored in configuration. So gravitational potential energy is the amount of energy stored in a configuration of masses. And the more you separate the masses from each other, because the gravitational force is attractive, so you can store energy against that attractive force. The same is true, for example, when you think about elastic potential energy, a rubber band. You stretch it, and by stretching, you're storing some energy. You let it go, it turns back into motion. Or you compress a spring, right? Now, a similar thing happens for electric potential energy, if you recall. If I squeeze like charges together because they want to repel each other, then I'm storing energy into that configuration. Or if I take a positive charge and a negative charge, unlike charges attract. So if I separate them, that means I'm storing energy against the attractive force, the attractive electric force. So now let's see how in today's story we can transform kinetic energy, energy of motion, into a separation of charge or electric potential energy. Now today's story starts with a conductor, a neutral conductor of length L, that is moving with some velocity v. Now since it's neutral, that means it has no excess or deficiency of electrons. It has as many positive charges as it has negative charges. Now as the charges are moving along with the conductor, nothing is going to happen to them. But if they encounter a region in which there is a magnetic field, let's say a uniform magnetic field that is pointing into the page like this, then the charges will experience forces. Let me remind you, if you recall, that any charge that is moving in a magnetic field will experience a force. The magnitude of that force is proportional to how big the charge is, how fast the charge is going, the strength of the magnetic field that it encounters, and the relative direction between the direction of motion and the direction of the magnetic field. Now what I care more about here is the direction of that force. If you remember, that's given by the right-hand rule that says put your thumb along the direction of the velocity, put the rest of your digits along the direction of the magnetic field lines, and then out of the palm of your right hand, there will be the force on a positive particle, and out of the back of your right hand, there will be a force on a negative particle. If we apply that logic to the situation that we have over here, here's what happens. If I put my thumb along the direction of the velocity, so that's parallel to the page, parallel to the screen pointing down, that's the direction of the velocity. And then the magnetic field is pointing into the page. So into the page, that would be away from you, into the page like this. Then that would imply that out of the palm of my hand, a positive particle would feel a force towards the right, and out of the back of my hand, a negative particle would feel a force towards the left. So this means that as the bar continues to move through the region where there is a magnetic field, then there will be forces on the positive charge that be towards the right, or on the negative charge be towards the left. So as the bar continues to move through the magnetic field, the charges then will separate. The positive charges are going to accumulate more on the right, and the negative charges are going to accumulate more on the left. Notice that it's not enough that the bar is in the magnetic field, that the conductor is in the magnetic field. It has to be moving. The motion part is very important because that's really what generates the force that separates the charges from each other. Now the next question you might ask is how much energy, how much electric potential energy is generated in this case? And we'll talk about that next, but what we would rather talk about, or the way we quantify it in this case, is we quantify it in terms of the EMF, the electromotive force, aka the voltage. So if you think about the separation of the charges here, yes, it happened by mechanical means, but it's similar to a battery, for example, in which the separation of the charges happens by chemical means. But this looks like a battery. This looks exactly like something that would be like this. And then you would have the positive on this side, and then you would have the negative on this side. So that means if I hook up any electrical device between the positive and the negative, then a conventional current would flow and it would power my device. Now, the amount of voltage or the amount of electromotive force that is generated by this story is exactly proportional to, so this is called the motional EMF because it's induced by motion. And that's the voltage that is across the two ends of that conductor. And it's proportional to three things. It's proportional to how fast this conductor is moving in the magnetic field. It's proportional to the strength of the field. The bigger the field, the bigger the EMF. And it's actually proportional to the length, or really the width of that conductor. So it's the length of the conductor in the direction perpendicular to the direction of motion. So the direction of motion is down, the length across of that. So it's not this part that matters, it's the part that is perpendicular to the direction of the magnetic field. So the motion EMF is just proportional to the speed, the field, and the length, or really the width, of the conductor across the magnetic field, perpendicular to the direction of motion of this conductor across the magnetic field lines. And of course its unit would be the same as the unit of the battery, which is the electric potential, which has units of volts. It's electric potential energy per unit charge, so it has units of volts, which is equivalent to joules per coulomb.